I'm Krystian Igras, and I'm the member of MI² group, the group that brings together the students and PhD students from Warsaw University and the Technical University of Warsaw. On a daily basis, I work as a data scientist in Epsilon Data Science company, the company that offers data science consulting. Also, I'm R programmer and T lover, especially the Chinese one. So let's start. Let's make short spike about what am I going to tell you about today. At first, I will start to bring you closer the issue of explaining black boxes and machine learning models. The next case is the theory about the solution that I prepared. After that, I will tell you something about the implementation of this solution that is called xspliner package and show a small demo about it. And after that, I will tell you a bit more about the MI² group. So let's start. Yeah, why should we explain? Yeah, the case of explainable black boxes is such important, especially because of the common usage of machine learning in our life fields. So the great proof for that is just the current conference where we can see how many life fields uses the machine learning and how great this usage is, but it causes some unexpected behaviors sometimes when we use the exact models. Also, we can realize that it can be especially useful for this example. We can see one of the cases in which explainable black boxes can be used. For example, when we use the machine learning for predicting the cure for the patient in medical field. So if we've got the patient that has some features such weight, age, headache, sneeze, and we can realize which features were the most important ones, then it gives to the doctor such trust for the model so that he can accept the output or not, accept the decision. So we can see this is the example from the LIME algorithm, the article about LIME algorithm that is quite popular in last, that was quite popular and is now popular in the usage. Yeah, as I told you, it can be also unexpected. The usage of machine learning can cause some issues. For example, it was popular case when Amazon used machine learning for automatic recruitment, and it showed significant bias between men and women. Also, it can be dangerous because we know cases when, for example, self-driving car of Uber killed the woman in the beginning of this year. So the great summary of this is the quote from Eliezer Yudkowsky, the popular American artificial intelligence popularizer. So by far the greatest danger of artificial intelligence is that people conclude too early that they understand it. So such accurate. Yeah. So how can we explain? There are two significant steps. The first one is thinking. If we want to explain the model, interpret the model, we need to find out the solution for that. So this is the popular issue nowadays. So we can see, for example, that many articles are created today to provide some solution about interpreting machine learning models. Also, the next step is doing, because the paper, the solution, is just the theory, so we need to give this theory a new life, for example, building some kind of software, and it is also done nowadays, as you can see on these results. Yeah, so now I will show you how the doing is with xspliner. I will explain you how the model works, and then I'll show you the demo. So, as we can realize working with machine learning, that there is such straight trend about between the complexity of the models and its interpretability. For example, the simple models are much easier to interpret, to understand how it works, how the decisions are made. So I think that xspliner is such the golden mean between the interpretability and performance. So what is the idea behind it? Yeah, the idea comes from Przemysław Biecek. I think you know him. And it states that we should use the trained model, the trained black box model, as the surrogate one, extract some information from this model, and build the simpler one that inherits some of the features or some of the information about this black box. So let's check the exact algorithm, how it works on this graph. So at first we build the black box that is a predictive model in this case. After that, we try to extract some marginal model responses from this model. That is the one-dimensional functions that each of them is signed for the separate feature that was used to train the model. After that, we perform spline approximation from these responses and build the generalized linear model that is based on transformed variables with the approximated splines. So this is the exact solution over here, and one feature is that the GLMs, the models that its response functions is additive, has the marginal responses just like these transformations. So, but what are these marginal responses? Yeah, actually, the xspliner provides two solutions, uses two solutions. The first one is partial dependence plot. So this is the formula for that. This is just the expected value of the response functions based on the marginal distribution over the remaining variables. So when we want to count the marginal response for x1 variable, we just count the expected value based on the marginal responses from x2 to just xp distribution. So this is the estimator in the below part of this. And how it is constructed? It is constructed just like that we freeze the value from For example, we want to count the PDP for x1 variable with the value of 17.5. So we freeze in a training set that value, and after that we treat the new data set as the just as the new data that we use to perform predictions. After that, we have for each observation one prediction and just count the mean of that. And when we want to count another value, we just freeze another value for this for this feature, for this variable. Okay, so this is one of the solutions. Another one is accumulated local effects. It is a bit complicated, more complicated than PDP, and is actually based on counting expected value for the first derivative of the response function. And after that, it is accumulated on the near neighborhood of this of the value that you want to extract. I will not show the exact formula for that because it's a bit long and complicated over here. But we can see over here the some difference on these plots, how both of them are calculated, and what can be difference when the variables have some interactions. So we can see that ALE works much better when the variables have some interactions. Yeah. Okay, so after we have this marginal responses, we just want to approximate the results. So we just perform spline approximations, and this is up to us how we can do it and what basis for approximations do we want to use. Yeah, but I will show you this in the demo. So let's start with that. As I told you, I'm R programmer, so I prepared the demo on R. Yeah. Can you see this? All right, great. So I will use the PDP package, that is the package that provides extracting partial dependence plots. And I will use the Boston housing data that is popular from the mass package, but over here it's quite different, but the features are the same. So we will build for this case the random forest model as our black box. Just the simple one. When we want to predict the median of the house value based on some 4 variables, and 2 of them are, two of them are the continuous one is factor, and one of this is integer. Yeah, we've got the factor, integer, the RAD variable, and cream and PT ratio as the continuous one. Okay, so let's build our black box. And before I start showing how the explainer, how are the results of explainer, I want to show you how are the steps built. For example, let's build at first the partial dependence plot. So we just need to use function partial from PDP package, pass them our random forest, our black box, and define which variable we want to plot. So if we just use this function, we get data frame with some results. One of them is the variable, the predictor that we used, and the second column stores the values of partial dependence function. Yeah, and one thing is that the cream is evenly spaced over the range of this variable from the training dataset. So now we have 51 points. If we want to plot, if we want to extend this amount of points, we just need to use grid resolution parameter. So now I set this to 100, and we have 100 evenly spaced points that that presents the values for response function. We can also plot the results and see how this function looks like. Okay, and I'll name this as effect, and in xspliner the response, the data frame that is response of the marginal response is called effect. Another thing is transition. The transition is just the approximation of the result. And over here, I use MGCV package that provides building generalized additive models. So I use this model for approximation. This is our response. And after we build the GAM model, we just can see on the different plot over here the approximation. And this is exactly what is in the background of xspliner. We can also check the S function from MGCV that provides a lot of possibilities for how we want to approximate the function. For example, we can choose over here the K parameter that is just the dimension of the basis, of the spline basis, or one of the most important parameters is BS that provides the type of splines that we want to use. For example, passing CR, we can use cubic regression splines. Okay, so now let's start with the xspliner. Let's load the package. And how can we use this package for this case? We pass the same formula that was used before for building random forest, and we need to use the XS symbol for the variables that we want to transform. So we have over here two continuous variables. So we want to use XS on crime and cream variable and on PT ratio. Okay, another parameter is just the model that we want to use for extracting the marginal responses. Okay, let's try. We can see over here the information about the model family. GLM can use different families for the response functions, and in some cases the black box also use this. So if the black box uses just specific distribution for the response, also the xspliner will use that one. So over here we use by default Gaussian and identity link function. Okay, let's see the summary of the model. We can see the formula that was used previously and have such information like the significance of the components or another statistic like AIC. Yeah, and how can we check the approximations? How can we check the results of the model? We can also for sure plot the result, and we can see over here that how were the responses and how does the approximation that was used looks like. We can see some oscillation with approximated the crime variable response. So we will fix this in a minute. Yeah, we can also choose specific variables that are of our interests. Yeah, also we can plot some other useful information, such plot the data from the training model. Also we can plot the derivative for the approximations that can be mostly used for our analysis of the final model. So we can see that the values of derivative are stored on the right part of this plot. Okay, but how can we use this model to realize if it can be treated as the approximation for the final one? We can for sure compare the values of predictions for both of them. So here is the simple heat map that provides the values. Oh, I don't think it is well seen over here, but yeah, maybe it is. We can see that for most of the observations, the values are similar. For example, we can see some clusters of observations that tends to have a similar pattern in predicting the model. But over here, we use just a little of variables. What if we extend this? So we'll do this in a minute. Before I will show you how can we customize the parameters of that and pass specific parameters for the model. The first is the effect parameter and transition that can pass some parameters both for effect and transition. The parameter effect allows you to pass the specific parameters that are used in, for example, calculating PDP or calculating ALE. Over here, we will extend the grid for the PDP to 100, just specifying it as list of parameters for the effect. Another one is passing some parameters for transition, and this is those are exactly parameters that are passed to S functions that I showed you before. For example, the BS parameter. So we over here specify to use cubic regression splines, and we can do the same for the second transformation for PT ratio variable. Okay, let's build a model. We can see again how the approximations look like, and for cream variable, we can see that this solution omits the oscillation that we saw before for this variable. Also we can compare the models and see this in another view while sorting the variables in case of one of them. So over here we can see that the models differs a lot. So we for sure need to make comparisons between both of them, looking at some statistics, or if we realize that the models are really different, we just can use xspliner as another model that we can use for our solution, and and to analyze this in that. Okay, how can we change from PDP to ALE? We just need to pass another parameter called type that is by default PDP for effect parameter. Also, the grid resolution for ALE is just the K parameter, so that we use here this one. And let's check, for example, the cream variable. We can see that the marginal model response is quite different, but the approximation is quite good. Also, let's compare the models as before, but we can compare also the previous one that was based on PDP by using compare with parameter. So we just need to pass the list of another models that should be used for comparison of the responses. And here we can see that the the model based on ALE approach, ALE marginal response, is quite similar to this from PDP, but yet quite different. Yeah, but for example, especially while working with machine learning models, we use a lot of features from the data. And in R, you usually use the dot formula. That is, you just specify the response that should we use for prediction, and we pass just the dot to use all of the variables from the dataset that it provides. How can it be used in xspliner? In this case, you just need to pass the one parameter that is model, so it automatically extracts all the variables from the black box and builds the final model. So in this case, let's try to build this one. Yeah, as we use here some more variables, it lasts a bit more. And yeah, we got an error. And why is that? If we come back before to the previous parts, we passed to this model some variables that are integers. So the spline approximations for them is not accurate because of less unique values, a low amount of unique values that it provides. So we usually want to omit such variables from transformations, so we can just use over here the bare parameter that stores all the variables that we want to omit while transformation. So let's try to do this. I excluded five variables over here. Yeah, we got the model built, and let's check how the formula looks like now. Yeah, we can see that XS was not used for the variables that I specified. Also, we can see that for the factor variables, we used mysterious function xf. I will not tell you about this today, but this is some solution that is used also for transformation of factors. And you can see, you can learn about this on the package page and vignettes. Okay, so let's check how this model looks like now. The comparison shows us now that there is no such quite differences between both of the models. Also, when we sort this one based on xspliner variables, we can also see over here that there looks more familiar, more similar in here. But how can we customize the parameters for the transformations and for the effects? In the case of passing just the model for automatic extraction of variables, we just can to specify parameters xs_opt, and for example, for this case, we want to pass the grid resolution parameter for the effect as 100, and we want to use cubic regression, so we pass the transition variable. In this case, the configuration will be used for each transformation and for each extraction of the model response, the marginal response. Yeah. Let's wait a minute, maybe less. Yeah, come on, guy. Okay, we've got this. Okay, and finally, we can, as we saw before, compare the models and decide how can we use this in a further analysis. Yeah, also, some of you can hear about the DALEX package that was created by Przemysław Biecek. It is the base for such bigger projects that is that is currently built by MI squared group that provides the specified object with some informations about the machine learning model. So the xspliner is also integrated with that one. The main function for the DALX package is the explain, and this is just the function that provides quite useful information and in some specified exact form the models. Yeah, after we have this explainer from DALX package, we just can use this just exactly as we saw before, with passing as the first parameter the explainer object. Yeah, and this is built also on all of the variables. When we omit, in this case, the four of them, actually the tax is also integer, but it has quite a lot of unique values, so the approximation also works for that. And after that, we can see that the effect is the formula that was used is the same. Okay, so this is the demo. More about the features that the package provides you can read on the page of this package. Yeah. So let me continue. As the last part of my talk, I wanted to tell you something about MI squared group. So this was created in 2015 by Przemysław Biecek, and the first part of data analysis that it was focused on, it was just the exploratory data analysis. Currently, we focus on explainable machine learning models and the solutions. So for now, currently we're working on Dr. White project that is something similar to Tidyverse, but it is for explainable AI. The Tidyverse is the universum of packages for R packages that are quite useful and has complex notation for all of the packages. It's quite popular, and we want to build such a set of tools that will be used for explaining the machine learning models. So for now, we have a few tools. One of them is xspliner that you saw before. Also, we've got factor merger package that was created from Agnieszka Sitko, that is organizer of this conference, and it used additive post hoc comparing for factors. Just for factors that were used in training the model. Also, the visual analysis of the model errors that was built that is provided by auditor package from Alicja Gosiewska. Leaf package, the model regression tools based on the LIME package from Mateusz Staniak. Also some model-specific solutions like random forest explainer from Ola Paluszyńska. And some more packages that are now in progress. Yeah, you can see the current state of our work on GitHub. Yeah, and after I finish, before I finish, I will encourage you to join MI Squared group. If you want to do something about thinking and about doing and have some contribution for explainable AI, you for sure will join us. Also, if you want to solve some interesting problems in data science, I encourage you to visit epsilon.com. We've got open recruitment, so I think it would be great if you join us. So thank you, and this is everything. If you have any questions, please ask.